Hi! Today we're going to learn about the integral test remainder theorem in calculus. Let's say we have to approximate the sum from n equals 1 to infinity of 1 over n squared with a maximum error of 0.1. So how do we do this? Well, before we dive into this problem, let's figure out a method for doing this. So let's draw a graph here. So the first thing is we should draw our series on here, or what we're trying to find the sum of. So here we can see we have 1 over n squared. Now what we have to know is that most series that converge are monotonically decreasing if they're positive, or monotonically increasing if they're negative. So basically what that means is it's always decreasing if it's positive, or it's always increasing if it's negative. And it's not always like that, like in the case of alternating series, but the point is that they all come closer and closer to 0. Or to some value. Yeah, 0. So, let's just draw some random function and try and figure out a way that we can do this. So, let's just say this function is positive, so we can get a bigger graph. So let's say it comes down like this. And so we want to approximate the series. So before we get started, let's first understand what we want to find. Well, we want to find the sum when n equals 1. So 1 comma x. The sum when it's 2. So let me rephrase this. So this is 1. This is 2. This is 3, let's just say 4 dot dot dot. So basically, we want to find the sum of 1 plus the y value of 1 plus the y value of 2 plus the y value of 3 plus the y value of 4 and so on until you get to infinity. So what it's going to do is when you have series that converge, these series which converge, which means that they essentially reach a number. So their sums just get closer and closer and closer to an actual value. So let's figure out how to approximate this value. So, we can see that if we took this sum here and added it with this sum, then we'd get the first two sums in the series. Now, if we see this, we can see that this is actually pretty similar to an integral. The only difference being that if we're taking the integral from here to here, we also have this area in between. That severely impacts the difference between, or that changes the value of the integral. So this area in between is basically why the value of the integral from, let's say, point A to point B is different than the partial sum from point A to point B of the series. However, if we use this logic, we can say that if we know what maximum error we want, and in this problem we know that we want 0.1 as our maximum error, then there will be some point at which, let's say, C, there will be some point C at which, let's extend this further, at which you have C plus 1, C plus 2, and so on. So you'll have some point C where when you start taking the integrals from that point onwards, the sum of all the areas, or the sum of all the integrals from that point to infinity will be less than 0.1. So that means that your your error will be less than 0.1. So that means that your approximation will be closer to the actual value. And you can change this maximum error that you want here. So let's figure out by changing what happens when we change this maximum error. So if we increase the maximum error that we want, then that means that C would decrease, right? Because then you would have more area that can fill up the error. So let's do an example of that. So let's say you want the error, let's say this is an error of like 0.99. Let's say you want an error of less than 0.3. So then maybe you can start from this point to D, and this area from which we know is 0.99 or we know for sure would be less than 0.1, plus this value here would have to be less than 0.3, I think that's what I said. So this would all have to be less than 0.3. So we can see that if we increase the max error, then we can decrease this value here. So this integral, or the area between them, has more room for error. So I hope you guys got that. But now let's see what happens when you decrease the error. And you might understand it a little better now. So when you decrease the error, then what essentially you're saying is that this value c, so let's say this was c over here. So when you decrease the error, you're saying that this area in between that you're adding, the total sum of that area is too much for the approximation. So you want less of that area added in, so that your maximum error will be closer. So let's figure out what this maximum error actually is. So we have these values, and there will be some in between here, and you're just continually adding them at each integer. But once again, because these are always coming closer to 0, there comes a point where this area in between these integers, the area in between of them, when it all added up from that point onwards to infinity, would be less than the error that you want. So that means that the approximation is within the maximum error of the actual value. So if this maximum error was smaller, then that means that this value, let's say d now, would have to be farther out. So we can take away these values, and if we subtract these from this total error, then our error will be smaller, right? So now let's figure out what changing this means. So far we've just been talking about moving this around. But how does that help us? Well, we know that it's really hard to figure out the actual value of a series, and that's what we're trying to approximate here. We also know, however, that it's really simple to calculate the sum of a partial series, or the partial sum. So what is that? Well, basically, it's just a series from n equals a constant a to a constant c. And we can just plug that into our calculator or do that manually of f of x. But this is really simple. So essentially, what we're saying when we have this value d is you can have, in our case, in this example here, you can have the partial sum of the series from n equals 1 to this constant d of 1 over n squared plus the integral from d to infinity of 1 over n squared dn. So this is essentially how we get our approximation. But there's a little problem here. So try and see if you can figure out this problem yourself, or how we can fix it. And I'm going to, no, actually I'm not going to erase the graph. Actually, I am going to erase the graph. Okay, so there really isn't actually a problem with this. This is how we find our approximation. But the thing is, this doesn't help us find the approximation, because you need to figure out what value d is. But how do we figure out what value d is? So once we figure out the value of d, we can just plug it into this equation, and that'll give us our approximation. But the part that we're missing, or the step that we're missing, is finding out the value of d. So first things first, let's get some things cleared out. So some notation that we're going to be using now is S is just the sum, whoops. So essentially S is just this sum, so you're just shortening it up to make it look cleaner. The next thing that you have to know is, yes, the S is the sum. The next thing that you have to know is S sub k is the kth partial sum. What that means is you have the sum from n equals 1 to k, the constant of 1 over n squared. So it's just telling you what value you're going to stop at. So let's just write that down. Kth partial sum. So now let's draw another graph and see if we can figure out how to find the value d, or now we're going to find the value k, which is basically the same thing, but k is a standard notation. So let's draw another graph to figure this out. So we have our monotonically decreasing function here. So let's say that we have these values, and let's say this is point k. Actually, let's move k so that's farther. Yes. So let's say this is the value k. And so we have k plus 1, k plus 2, and k plus 3, and then so on. So if we have k, and we take the integral from k to infinity, then basically using the Riemann sum, which we know from Calc AB, we basically are just doing this. We take this entire sum and then add it to this area. And because these are just 1, that the areas or the widths are 1, you're just finding f of k plus f of k plus 1 plus f of k plus 2 plus f of k plus 3. And so we can see, in this case, that we're overestimating the value of this integral. So we're overestimating it. So let's just write that down here. Overestimate when we have the integral from, I don't know if you guys can see that because that's too small, when we have the integral from k to infinity of f of x dx. Now let's draw a different scenario. So we have the same function, let's see, right here. This is k. Let's just assume this is the same function. It doesn't look anything remotely close, but let's just assume that. So this is k. This is k plus 1. This is k plus 2. And this is a terrible graph. And this is k plus 3. And so on. So now let's say that, and in this case, we can see that we're taking the left Riemann sum. Basically what that means is we're going to the y value of the left edge of this rectangle and then taking the area of the rectangle. Now let's take it with the right Riemann sum. So we go like this over here and we find the area of this rectangle. We find the area of this rectangle. We find the area of this rectangle. So let's understand what we're doing here. So in this case, we have an underestimate. And that's easy to see because we're just missing these areas. Underestimate. Oh, I did not spell right. Underestimate. But this time the integral is a little bit different. This time the integral isn't from k to infinity. We have the integral from k plus 1 to infinity of f of x. And so we can see that because we're taking the height of k plus 1, then making this rectangle, and then k plus 2. So we're not starting at k like we were in this example here. But now let's notice one key thing when we mix these graphs together. So this one really key thing, which is actually very obvious, is that this graph, when we start from k to infinity, is an overestimate, and when we go from k plus 1 to infinity, it's an underestimate. So this is really important, because if we know the partial sum from s sub k, so let's write this down. So if we have the partial sum s sub k plus because this is an underestimate, let's do it on the left side, and you'll see why. I'm going to have to erase something. So, make sure you got these down in your notes, because they're going to leave now. Okay. So let's write this down first. So you have the partial sum up till this value k. So you have s sub k. Remember, it's a partial sum till k, plus the integral from k plus 1 to infinity of, in this case, in our example, actually let's not use our example yet, of f of x dx. And so we know that this will be an underestimate of the actual value of the sum, or of the actual sum of this series. And so let's go over why that's true. So this will be less than or equal to s, which is the sum of the series. So let's go over why this is true. So we know that when we reach this value k, from here on to infinity, the sum of all the areas, including this little triangles that we're missing here, the sum of all that area will be less than or equal to our max error that we assign. In this example, it's 0.1. And same for this here. Except when we have this overestimate here, we have from k to infinity, the area is less than or equal to 0.1 when you subtract these values at k, k plus 1, k plus 2, k plus 3, because those are actually included in the series. So that sum will be less than 0.1, but that's when we don't include these overestimates here. So basically, what we're saying is this underestimate will be less than or equal to s, which is the sum of this series here. Now s will be less than or equal to the overestimate. S will be less than or equal to s sub k plus the integral from k to infinity of f of x dx. And so this is really, it's easier to see now. So basically what you can see is when you're starting at a term farther out and it's monotonically decreasing, when you're starting at a term farther out, you're missing this area here. So that's why this is lower, or this is smaller, which is in this case, this is smaller than this value here, which is the overestimate. So just imagine that these two graphs were swapped, or swapped places, so that this is correlating with that. Let's just draw an arrow. This is correlating with that, and this is correlating with that. So take a moment to copy this in your notes, because now the graphs are leaving. Okay. So now we're going to define a new term here. So this new term is called, or is, r sub k. So r sub k is the remainder at the kth partial term of when we stop at k for our partial sum. So basically, r sub k is just our error, our actual error. So let's see if we can figure out what r sub k is given this. Well, it's simple. R sub k, the max of r sub k, max of r sub k is equal to, now before we move on to this, let's establish one thing here. So this is the sum of this series. This is above it and this is below it in terms of value. So basically what this means is this is an upper bound to the sum and this is a lower bound to the sum. So we know that the sum for sure is going to be less than this and greater than this. So now let's figure out what the maximum of r sub k is. So because we know that the sum for sure is less than this, and the sum for sure is greater than this, then that means that the maximum value r sub k can be is this value minus this value. So let's just do that in our heads. So this minus this. we can see the s sub k's are going to cancel out. So we're going to be left with the integral from k to infinity of f of x dx minus the integral from k to infinity of f of x dx, and I made a mistake, minus the integral from k plus 1 to infinity of f of x dx. So that's just what r sub k is. And so given this, the next step would just be to solve both of these integrals, and they're improper integrals, so you have to remember how to do that. So you just solve both of these integrals, and then you set this value, so you know this value can be at max, according to your problem, 0.1. So you set whatever you get here equal to 0.1. So that way you can find the k value by intersecting the graphs on your calculator. So you can find the k value where the error will be 0.1. So if you know the k value where the error is 0.1, then you can just go up to the next integer, because you can't have a series to not an integer. So you go to the next integer, and then your sum, if you use that as your partial sum, if you use that for k here, or in this example here, then it's going to fall within the error range that you gave it, which is 0.1. So I know this sounds confusing in words, so let's just solve it in our problem. So instead of erasing this, let's just go ahead and plug in our values. So we have the maximum value of r sub k would just be the integral from k to infinity of f of x dx, which is 1 over n squared dn, minus the integral of k plus 1 to infinity of 1 over n squared dn, which gives us, now if we do this, now I'm not going to do the limit of t or anything like that because we are running low on time. So this is equal to negative 1 over n, infinity, and k, minus, yes. So you can solve this integral yourself. I'm running out of space also, so I will just write down the answers. So take a moment to solve this integral. And if you don't remember how to do improper integrals, then you can watch the video on improper integrals quickly, or Google it up. So basically, this would turn out to be negative 1 over infinity is 0, minus negative 1 over k becomes positive 1 over k. 1 over k minus positive 1 over k plus 1. So minus 1 over k plus 1 is our answer. So basically, we have the maximum value of r sub k. So we're done, right? Well, not really. So here we just have this function here. We don't actually know what k is. But we do know that this error will have to be less than or equal to 0.1. Because in our problem, we're given that we want a maximum error of 0.1. So this will be less than or equal to 0.1. So the next step is to just set this equal to 0.1 and plug both of these functions into your calculator. So one of the functions is 1 over k minus 1 over k plus 1, and the other function is just y is equal to 0.1. So do that quickly. And I've already done this in my calculator. Oh, and we're forgetting one step. So one important step is to realize that when you have a maximum error of 0.1, that means that you can go 0.5 above, or no, not 0.5, 0.05 above the actual sum, or 0.05 below the actual sum. So basically what that means is you want the absolute value of the max error to be equal to 0.1. So, when you plug your function in, or whenever you have this maximum of r sub k, you always want this to be the absolute value. So this absolute value should be equal to 0.1. So plug that into your calculator. And you get, delete. you get graph. And you might have to zoom out a few times to actually see the intersection. Okay, so you get that this value is equal to 2.7. So k is equal to 2.7. But is that what we should use when we're creating our partial sum? Well, no, we should just round to the nearest, or not to the nearest, we should round up to the next integer. So let's just say that k would be 3. And in fact, this would actually be more accurate than 2.7 because you're extending your partial sum further. So anything greater than 3 would just be even more accurate. But the problem asks for a maximum error of 0.1, so we're just going to go as close to that error as possible. And let's say you wanted a maximum error of 0.0001, you would just set this equation equal to 0.0001 and find the intersection, or solve it. Okay, so now we get to the final and last step of this equation. Just plugging this value in. So basically, we have to do the sum from, oh boy, we have to do the sum. Wow, I don't have any space. Okay, so try and do this on your paper first while I figure out a way to get more space. Okay, so I hope you got this section in because now I'm going to have to erase this for more space, and this, unfortunately. So if you didn't get that, then go back and pause the video. Okay, so we have k is equal to 3. So let's just plug that into this equation. So we can plug it into either this lower bound or this upper bound. It doesn't really matter. Both of them are going to fall within the 0.1 maximum error from the actual sum. And what I said earlier about the 0.05, that was incorrect. The actual error it can be 0.1 below as a maximum error or 0.1 above as a maximum error, because you only have one approximation. So let's do this. We have the sum of n equals 1, 2, 3, which is what k was equal to, of 1 over n squared, plus the integral, let's just use this one here because it's simple, just k, 3 to infinity of 1 over n squared dn, which is equal to, so you can't exactly put this improper integral into the calculator, but it's pretty simple. It's just 1 over 3, and you can solve that for yourself. So you put this in your calculator. To get this sum here, you have to press second, or no, you don't press second. You just press math and go to number 0 for the math section right here. So you get summation and then the sigma. And so you get, so we have n is equal to 1 to 3 of 1 over n squared plus 1/3 and so this gives us a fraction. Let's convert that to a decimal. This gives us 1.694444. Let's just round that to here. Okay, or not rounding. So we get 1.694444, continuing forever. So the actual value of the series, okay, so let's circle this answer because this is the actual answer. So we have 1.694, repeating, is the approximation which falls within the maximum error range of 0.1. And the only reason we know that is because the actual sum of this series is pi squared over 6. which is about equal to 1.644 or 1.645, something like that. But we can see that obviously this falls within the 0.1 maximum error range. This is within 0.1 from the actual answer, so we can see our approximation is correct. So, this is how you do the integral test remainder theorem in calculus. Thank you for watching this video.